So can anyone tell me if the presentation is properly seen and if you see the laser pointer?
It's fine.
Fine, good. So first, it's not you who should thank me, it's me who should thank you, Andrea. Thanks for inviting me to this workshop, and it's really a pity that I cannot attend. My previous visits to the GGI have been an enormous pleasure, and I hope that I'll have other chances to come in person. So what I was thinking is to tell you today about topology versus interaction. And most of the talk will be about a recent piece of work I've done with Ady Stern with the Technion and Erez Berg with my colleague here at Weizmann. But there will be also, I'll remind you of earlier work from the past. My plan is this. I'm going first to give you the context. And the context is we're going to talk about a system of electrons on a lattice where, as long as you have no interactions between the electrons, there are topological features that force the spectrum to be gapless. And the question we are going to ask is whether by the time you add interaction, can you in principle gap the spectrum which you are not able to gap without interaction. So I'll start with two warm-up examples. One of them is kind of easy, the other one a little bit less. The first one is going to be about the chiral edge of in the integer quantum Hall effect. And the question would be, the integer quantum Hall effect or the Chern bands are non-interacting phenomena. Suppose that you add interactions, can you gap a chiral gapless edge mode? And the answer is no way. And I'll remind you why. The second example, which is less trivial, is the example of a Dirac cone on the surface of a 3D topological insulator. And there what I'm going to explain is that in principle, there may be a possibility to gap the Dirac cone on the surface of a 3D topological insulator, but as I wrote it here, it will cost you. And I'll explain what the meaning of the word cost here. I have to admit, I prepared this slide while I was carrying out renovations in my apartment, and I heard this answer to the question of whether something is possible quite a bit. So it was useful. Then I'll go to the main subject, which is fragile topology. Can interactions gap Dirac cones which are protected by fragile topology? And so I'll explain what is fragile topology. It also is relevant to a very hotly discussed context of twisted bilayer graphene. I'll explain what keeps the Dirac cones in fragile bands gapless, and I'll ask whether they can be made gap if we turn on interaction. Okay, now I should say, you're free, at least as I'm concerned, you're free to ask questions whenever you want, and don't talk to my picture on the blackboard. Okay, so that's the question, and the motivation for this question: can interactions gap a spectrum that topology wants to keep gapless? The motivation is twofold. First, there's a question of principle. Is it possible in principle? And then there's the context of magic angle twisted bilayer graphene in mind. So first example, as I said, there are two warm-up examples. So, think about the integer quantum Hall effect or just a Chern band with a Chern number. It's going to have a chiral gapless mode that's running around, and it is essential in order to have the whole conductivity quantized. Now what we'd like to ask is what happens if we turn on interaction. So clearly, the integer quantum Hall effect as a physical phenomenon can survive the presence of a weak interaction. Strong interactions may lead to a transition to a fractional quantum Hall state and all that. That's wonderful by itself, but I'm not going to talk about it. So weak interactions keep the state an integer quantum Hall state. Another question is, suppose that I turn on interaction here somewhere at the edge, can I get this gapless state? And the answer is no way. And to see that is, one way to see that is, imagine that I put in this way of gapping only in this corner of the system. Then I'm going to have a gapless spiral mode here that's flowing into oblivion, into a place where that's fully gapped. And this gapless mode carries energy, carries charge. Where would it go if it's all gapped? So the answer to this first example is no. Interaction cannot do that. Second example, as I said, is slightly more interesting. And this is the example of a three-dimensional topological insulator. So what is a three-dimensional topological insulator? It's a three-dimensional band with a time reversal, spin-full time reversal, a time reversal that's anti-unitary and squares to -1. And for certain bands, that three-dimensional bands that have this symmetry, there would be a gap in the bulk, but a gapless Dirac cone on the surface. So the question is, can interactions gap the surface Dirac? Now, I should say that there's this Dirac cone is protected by this time reversal symmetry and also by charge conservation. So if you bring interaction that spontaneously break a time reversal or charge conservation, then this doesn't count. Of course, you'll get the surface because you broke the symmetry. The question we want to ask is, can interactions get the surface Dirac cone without breaking the protecting symmetries, neither explicitly nor spontaneously? And before I give you the answer, it's a good point to introduce the main player, which is the Dirac cone, which is also a main player in the rest of the talk. So a Dirac cone is a touching point of two bands. Since we have two bands, we have an Hamiltonian that's 2 by 2, and very close to the Dirac point, we can write this Hamiltonian in terms of Pauli matrices because it's 2 by 2. So kx sigma x, ky sigma y, and a mass term times sigma 3. If the mass term starts as a constant, then there will be a gap here. But if it's absent or it starts or it's 0 at the Dirac point, then there won't be any gap, and it will be a touching point like we see. Now, if there is a mass, then the sign of the mass and the relative sign of these two terms will tell us what is the sign of the Berry curvature that's carried by this bottom of the blue band or top of the red band. So there will be some Berry curvature that sums up in the case where this mass is very small. It sums up to half of E squared over H, but whether it's plus half or minus half depends on the relative sign of this M0 and the product of basically these three signs. The sign of M0 times the sign of these two terms. That's the Dirac cone. And now we'd like to know whether we can get. Now, as I said, in the case of a three-dimensional topological insulator where we have just a single Dirac cone on the surface, this Dirac cone is protected by time reversal symmetry and charge conservation. And it will be helpful for our discussion to discuss what happens if you break those two. So let's imagine that we break time reversal by introducing a mass term, which is basically like introducing a magnetization. And we take two signs of the mass term, which are opposite to one another. So on one side, we will have a Berry curvature or a whole conductivity of E squared over 2H. and on the other side of minus E squared over 2H. So there's a difference in all conductivity of 1 E squared over H, and therefore there will be a gapless mode that will, a chiral gapless mode that will flow, let's say, in this case, upward. And of course, if I make this breaking of time reversal only here and here, and the rest of the surface around is not ME0, then the rest is just gap. But now let me add another breaking. I'm going to break charge conservation by coupling here to a superconductor. So that's fine. There will be a gap here because I broke another thing. And what's going to happen to this chiral mode is that it will split to two, which will go chirally 1/2 to the right, 1/2 to the left. Now, what do I mean when I say 1/2? This is a non-interacting chiral Fermi, one-dimensional Fermi liquid, which means it carries a central charge of 1. And at this point, this central charge will split into half here and half here, which would mean that that there's a central charge of 1/2 going in each direction, which would mean that this will become a Majorana mode. But that's fine. It's a Majorana mode at the edge of a superconductor. So a superconductor, of course, can carry Majorana mode. Now, I asked whether there are interactions that can gap the surface Dirac curve. And before answering this, let me answer something that's related, but not quite the same question. And I'm going to show you that if such a mechanism to gap the Dirac cone without breaking of any of the protecting symmetries, if it exists, it will involve topological order. The state. So I'm going to say that if I replace the superconductor, which was charged non-conserving, by a gap state that's time reversal symmetric and charge conserving, the state of the structure of the edge cannot change because here nothing changed, and this will have to break into two halves because of time reversal. So I'm going to have a Majorana mode flowing between the magnetized region and the time reversal symmetric gap, a Majorana mode. But now this Majorana mode does not flow on the surface of or at the edge of a superconductor. It flows at the edge of a charge conserving state. And we know that the Majorana mode at the edge of a charge conserving state implies topological order. Implies that this state will have non-abelian statistics, downstate degeneracy, so on and so forth. So this is an observation we made in this work that I'm involved in. And then after that, indeed, there were ways found in this work by Anderson, Monk, and Mitlitsky and their collaborators. There were ways found to gap the Dirac cone on the surface, and indeed by generating a topological. Now, so this is the strong TI, if you want, in the title of my talk. I won't say much about the weak TI that was analyzed here, but in the weak TI there are two Dirac cones. They are confined to time reversal symmetric points at the brilliant zone of the surface, and you can gap them by having fractional excitations of an abelian type, but still by having topology. Okay, so far. Okay, so now I told you about my two Hormone examples, and now I'd like to discuss the third example, which is the one I'm going to spend most of the time on. So the question is going to be now, can interactions gap the topologically protected gapless spectrum topologically fragile band? And if so, motivated by the example of the topological insulator, I'd like to ask, is topological order essential? And as I said, this was book done in a very enjoyable collaboration with Erez and Ari, and that basically started with Erez and me trying to prove that topological order is essential. And just when we were almost proving it, Ari came along and corrected us and directed us in the direction of.
Okay, good.
Sorry. Can I ask something, Ady? Sorry, I was muted. Hello.
Yeah, I hear you.
Yeah, right. So actually, I think before when people discuss whether the boundary of a topological insulator or topological superconductor is gappable or not, people actually check whether the boundary has a perturbative to Hoover anomaly or not. If it's a perturbative to Hoover anomaly, it means that it has to respond. It has to respond to a very small, very weak external gauge field. That means that actually it cannot be gapped. Yeah, well, but if it's a global anomaly, it actually does not have to respond to infinitesimal background field, so it can be gapped into a topological order. This is this is anomaly matching condition. So I wonder what kind of anomaly matching condition that we can apply to the fragile topology in this language.
Okay, so what I'm going to we'll get to that because I haven't yet introduced the fragile topology. But to make a long story short, I'm going to show that you don't need topological order if you want to gap a fragile band. Another way of saying it, it lives up to its name. It is indeed fragile, and interactions can gap it.
Oh, so you are saying it's completely trivialized by interaction. It
can be trivialized by interactions, right? It's not easy to see it, but I'll show it in the rest of the talk. But that's what I'm going to show. Yes.
Okay. Thanks.
Okay. So judging by the picture I see on your screen, your kids are listening too. Right, thank you.
Oh, sorry?
Judging by the picture I see on the screen, your kids are listening also.
Oh, yeah.
So, okay, good. So first what I'd like to explain is what fragile bands are. And I'm going to mostly focus, this is a concept that was developed in the last few years by several groups, the Harvard, Princeton, Hong Kong, Cambridge, other places. I'd like to focus here on one aspect, which is fragile bands are a pair of bands that are connected to one another by 2D racons, which are protected by some crystalline symmetry that protects the fragility. Now, so I'm going to introduce this, but let me emphasize right from the outset 2 things. First, unlike the previous 2 examples, this is going to be a standalone band structure. So a 2-dimensional band structure that you can realize not on the surface of a 3D state, but just a standalone. And second, I'm telling you about 2D racons. Immediately you can, excuse me, you can bring up the association of graphene, but there's a difference, and I'll highlight this difference. In graphene, you can bring the 2D racons close to one another and just gap them by proximity. For example, by straining the hexagonal lattice very, very strongly, you will be able to gap the 2D racons. to bring them from the K and K prime point to touch one another. Here that's not going to be possible because the archons, as you will see, will carry the same chirality, and I'll explain what that means. So let me start by constructing a pair of fragile bands. And I'm going to do it in the following way. I'm going to take two pairs of Chern bands. One pair is going to have a low energy band with a Chern band of +1 and the high energy band with Chern band of -1. And the other one will have the opposite, a lower energy band with a Chern of -1 and the higher one with Chern of +1. Now, what we're going to do is we're going to put the chemical potential here or even below. Basically, we're going to send this gap to infinity and completely forget about those two bands. And then we're going to couple those two bands and see what happens. But actually, before doing that, let me say a few words about each of the two pairs. So about the blue ones only or about the red ones only. So if we think about a pair of Chern bands, a lower energy one and a higher energy one, each one of them carries a quantized Hall conductivity, which is either plus or minus the Chern number times E squared over H. The wave function for each of these two is a two-component spinor because it's two bands. And it covers, and this is an essential property of the Chern bands, the wave function covers as you change momentum, you find that the wave function will cover every point on the Bloch sphere. So the wave function being a two-component wave function covers points on the Bloch sphere, and as you change K, you will traverse every single point on the Bloch sphere, and that leads to the fact that there is no gauge choice in which the wave function is smooth. These are general properties. Just to take an example, this is a band structure that basically does this. You have sigma z, sigma x, and sigma y. You see that you have a gap Dirac cone near the gamma point, and if you don't see it immediately, you can expand close to the gamma point, and then it looks like the gap Dirac cone we talked about before. The wave function is a two-component wave function, and there will be, because of this point, singularity as you approach the point where the sign is 1. There won't be a smooth limit, and this is this point that I was making before. So this is just two bands, one with a Chern band of -1, the other one with +1. If we want the two pairs that we talked about before, we now have 4 bands. So now we will need 2 Pauli matrices, and tau z will distinguish between the blue pair and the red pair. Now, once we have the 2 of them, and this one has a Chern number that's opposite of this one, the total Hall conductivity will vanish because -1 and +1. There won't be a total vorticity of the wave function. I'll come back to this. And the final state that we will get will depend on the way we will couple those two. If the coupling satisfies time reversal symmetry, spinful time reversal symmetry, namely anti-unitary time reversal that squares to -1, then we get a 2-dimensional topological insulator, which is an amazing state by itself, but it's not what I'd like to talk about today. So what I'd like to talk about is that we are coupling the 2 bands that we saw before. We are coupling them to one another in a way that does not preserve spin-full time reversal symmetry, but preserves a different symmetry, which is the product of C2 times time reversal that squares to +1. So it's an anti-unitary symmetry because time reversal is always anti-unitary, and this is a crystalline symmetry. C2 is rotation by 180 degrees. It's an anti-unitary symmetry, but let me dwell a little bit on what it is. So if we think in real space, time reversal by itself is complex conjugation times some local operation. In momentum space, it means you take k to -k. You reverse the sign of the momentum. If you so this is time reversal. Now, C2 in real space takes R to minus R, and in momentum space takes K to minus K. The product of these two in momentum space will, one of them will take K to minus K, the other one will take minus K to K. The product is local in momentum space. And this is what will protect the Dirac cone from gapping, because it's a symmetry that acts at the point where at the Dirac point itself. So the product C2 times T plus is local in momentum space. It's not local in real space. It's local in momentum space. It's anti-unitary, and it squares to +1 because those two, it turns out, commute with one another, and it squares to +1. Now, this symmetry, as you will see, will be capable of keeping a Dirac cone from gapping. A symmetry cannot create a Dirac cone, but it can at least make sure that once it exists, it will not be gapped. So to see that, imagine that we have a Dirac cone. We'll understand why in a minute, but imagine that we already have one. And it's somewhere in this subspace that's spanned by these two bands. So we have a two bands subspace. We can describe it in terms of a set of Pauli matrices, which are the set, they are not the sigma or the tau we had before. They are the set that span only these two. So this symmetry will forbid one of the Dirac matrices. In the simplest case, when we're just complex conjugation, it forbids eta y. Otherwise, it will forbid one of the others. I'm going to use a basis where eta y is forbidden, or use a representation where eta y is forbidden. Then the Hamiltonian is real. And then it will be the sum of H0 of K, which we don't care about, but plus this structure, which basically has eta z and eta x in it. So you cannot introduce a mass term to Dirac to gap a Dirac point if it exists, because the mass term would have to be proportional to eta y. Now I'd like to argue that indeed there must be not just one but two Dirac points in this structure that we built out of these two Chern bands of opposite Chern number. Let me explain in the following way. So look at this Hamiltonian. It's basically I can write it as a two-dimensional vector, real vector, because H1 and H2 are real. So H1 of K and H2 of K are just a two-dimensional vector that's a function of K, real vector. Now, let me ask, if I pick a point on the torus that forms the Brillouin zone, I pick a point K0, and I ask, does the vector H wind around that point? There may be two reasons for a positive answer, that there is a winding. First is that there are Dirac points at or within the trajectory that I'm taking around the point K0. That's one reason. But there's another possible reason. And the other possible reason is if there's a singularity in the basis vector of the two lower bands, right? Because those two lower bands are now not spanned by sigma and tau, which were Pauli matrices that corresponded to local degrees of freedom. Those are now, those etas come out of a projection to a subspace of two bands. And that projection may have a singularity. In fact, when those basis vectors are basis vectors of Chern bands, they must have a singularity. This is the point we made before, that we said that you cannot have a gauge where the wave function is smooth. So as a function of K, there must be points where the wave functions, the basis vectors for this projection have singularities. And in those situations, at those points, there will be also a singularity in H1 and H2, but that's a singularity that does not imply a Dirac point. It simply comes out of the need to cancel the singularity of the basis vectors. So those are the sources of windings. Now, overall, over the entire torus-shaped Brillouin zone of K, there cannot be a total winding because it's a periodic vector. So the total winding must vanish. Now, there must be a singularity in the basis vectors, a winding coming out of singularity of the basis vector, because we combine two Chern bands here. And therefore, to cancel this singularity, there will have to be two Dirac points. And indeed, if you diagonalize the Hamiltonian of H1 and H2, the Hamiltonian projected to the two lower bands, you find two Dirac points. And what you see here is the phase of this vector H1 and H2. That phase has its own winding because of the singularity, and the position of this winding can be moved around by a gauge choice. The position of the Dirac points is a gauge independent quantity. It has, of course, a physical significance. Now, we can, so there's a winding of age, of the vector age, as we go around the two Dirac points, which means that we cannot just gap those two Dirac points by bringing them close to one another. What will happen if we bring them close to one another is that if we bring them to the same point, instead of having a Dirac point plus a Dirac point, we'll get a quadratic band touching where the winding is just double the winding of the Dirac one. So this is the construction of these two Dirac points, which come out of a gap of a coupling of opposite number Chern bands in a way that preserves C to T plus symmetry. And now we can ask, okay, can we, excuse me, constrained by this headphone. We can ask, can we gap these two Dirac points in some other way? Of course, if we break C to T plus symmetry, then these Dirac points are not protected anymore, and we can introduce a gap term, a mass term that goes like eta y. But can we gap these Dirac points without breaking C to T plus symmetry? But before answering this, first let me make sure that the quality of the sound is still fine, that you haven't lost me. So please tell me that it's okay.
Keep going.
It's okay? It was also a good chance to think something. So what I'd like to say now, which was pointed out by the pioneers of this field, which I mentioned before, is that if we bring a third band, even a trivial one, we can gap this quadratic band touching. And let me show how this happens. It's actually nice to see. So this is our H1 and H2 of a quadratic band touching. Phi k is the magnitude of the k vector. I'm expanding close to this point, and phi is the angle of the k vector with respect to the x-axis. So this is nothing but kx squared minus ky squared, and this is 2kx ky, and divided by some mass. So this is just an expansion of a quadratic band touching point. Now we bring a third band, which is just a trivial, one atom unit cell band with a dispersion of epsilon 0 plus k squared over 2n. What I'd like to explain, excuse me, is that if we couple this band to those two, we can gap this, or we can detach the lower band from the upper one. And the way to do that is by coupling them, of course, and you can convince yourself that this type of coupling of kx here and ky here will lead to basically will gap these points here and will make this, you see it here, will make this lower band detached from the upper two. So we brought this extra band, we couple this extra band to the original two, and we detach the lower one from the upper two. Now, you see that we don't do much at large Ks, but close to the gamma point, we basically replace the lower band by the blue one, by this coupling. Now, it's easy to see that you cannot gap in this way a single Dirac point, because for a single Dirac point, you would have here cosine phi, here sine phi, and therefore correspondingly, here cosine phi over 2 and sine phi over 2, and that would make this a non-local coupling. So it would not be a possible way to gap a single Dirac hole. Basically, I should say what we did by adding the third band is now the Hamiltonian is still real. It preserves C2T plus symmetry. So you can think of the Hamiltonian as a vector in three-dimensional space. And now you don't have to have a winding. You can resolve a winding by going to the third dimension. So the bottom line of this is, and this is actually why originally fragile bands were called fragile, because by bringing a third band, even a topologically trivial one, you can gap the other two. Now, as I said, what I'd like to explain is what happens when you turn interactions. So now we got to the point where we turn interactions. So we'd like to, we'd like to show that by introducing interactions, you can trivialize the lower band and detach it from the other two. But in order to do that, I need to specify the rules of the game. So we have these two bands. So now that we turn interactions on, we have these two bands that you see here in red. We are not allowed to bring a third band. What we have is just the subspace spanned by these two bands. That's what we have at the non-interacting C2T symmetric level. We have these two Dirac points. Now we would like to turn interactions on, and there are things we are allowed to do and there's things we are not allowed to do. We are not allowed to break C2T symmetry or any other symmetry in the problem spontaneously. We're not allowed to do that. We are allowed to introduce interactions whether Coulomb thought about them or didn't. We don't care about that. We're allowed to introduce any local interactions. And we're allowed to change the band structure at the non-interacting level as long as we keep all the symmetries. We are not allowed to add any external degrees of freedom from other bands. The degrees of freedom we have are only those two bands which we introduced before. So the idea is somehow to use what I told you, that by adding a third band we can gap or we can detach the lower band. We'd like to use this mechanism by somehow using interactions to form a new band of low momentum fermions, which are constructed from high momentum degrees of freedom in the two bands below the chemical potential. And then we'd like to use interactions to construct this kind of composite fermions, and then have these new fermions interact with the old ones in such a way that gaps the lower band. So the source of inspiration we have for this is the effect of interactions on gapped bands in semiconductors, and there are two types of effects which are well known in the world of semiconductors. First is interactions can form what's called the excitons, which are bound states of one electron and one hole. Therefore, since they have one electron, one hole, they are bosonic, and they have a binding energy. Now, given that they are bosonic, they're not what we want. We would like to have a band of fermions close to the gamma point. So in fact, we'd like to avoid those as much as possible. Now, the energy of the exciton is just the sum of the electron state we take from here, the whole state we take from here, and some binding energy which comes out of interactions. I see that there's a question, so let me, I'm taking it. Shantonu asked, why are we interested in gapping a Dirac cone? What is the physical significance? So thanks for this question. And I'll stop the introduction of how we gap to answer this question. So there are two reasons. First, at the level of principle, we're trying to understand what topology, how powerful is topology in forcing on topological systems various properties. And surely Shinsei will talk about that tomorrow in a review talk. But sometimes topology forces us to do certain things, and we'd like to know whether in the fragile case topology is strong enough to disallow us from gapping the spectrum. More specifically, in the case of twisted bilayer graphene, there are fragile bands. I'll talk about that in a few minutes, particularly if Andrea will be liberal in his way of looking at the watch. Then I'll talk about that. I won't need much more than 10 minutes, but in twisted bilayer graphene, there are fragile bands, and the charge neutrality is gapless at the non-interacting level. And the gaplessness is protected by exactly this C2T symmetry. Now, is it a gapless or gapful in real life? There are experiments showing this and experiments showing that, and probably it's gapped in certain conditions and not gapped in others. Now, how come it's gapped? If I told you that there are gapless Dirac points which are protected by C2T symmetry. So one possibility is that C2T is broken spontaneously by interactions and the spectrum becomes gapped. But what we'd like to point out is that there is also a possibility to gap the Dirac points without breaking the symmetry. So that's what I'm going to show now. So if that's okay, I'll go back to the discussion of the way to gap. So what we said is that there are excitons which are bosons, but there's another type of bound state in semiconductors, and that's called trion. And those play significant role in various narrow gap semiconductors. A trion is something that's made of two electrons in one hole, or two holes in one electron. It's basically like a negatively or positively or negatively charged hydrogen atom or a positively charged helium atom. So 2 electrons in one hole or 2 holes in one electron. This is a bound state. This is a fermion. And that's going to be the one that's going to help us. Oops. So I jumped too far. So as I told you, we're allowed to change the band structure at the non-interacting level as we want, as long as we don't break the symmetry. So the way we'd like to do it is we'd like to change the band structure in such a way that it will include 2 electron valleys, if you want, or minima anyway of the conduction band, one here and one there, and one whole valley here, whole pocket here, electron pocket here, and electron pocket here, in such a way that the sum of the momenta here minus the momentum here will be close to 0. So if we take an electron from here, an electron from here, and a hole from here, and bind them together into a trion, it will be a fermion, because, 3 fermions. It will be a fermion, and it will have close to 0 momentum. In fact, that's the one we are going to use to construct a low energy band of by interactions. So we introduce an interaction between the hole and the electrons, and it's an attractive interaction, and we find a trion whose energy is twice the energy of the electron plus the energy of the hole minus twice the binding energy, because there's a binding energy from the hole to each electron. Since we, this is a discussion as a matter of principle, we construct the interaction to help us and not let electrons repel one another. But in fact, we know that a negatively charged hydrogen ion exists. So that exists even in real life. So we need the trion energy to be negative and the exciton energy to be positive. And there's a certain inequality that needs to be satisfied, which means that the binding energy cannot be infinitesimal. So there's a threshold level of interaction that we need. Now, once we have this band of trions, this is a creation operator of a trion. It creates a hole, an electron in the first pocket, an electron in the second pocket, with some function that we can tune by the details of the interaction to be a localized function. Then if this function is localized on a scale that's smaller than the distance between the trions, so as long as the density of the trions at the ground state is non-zero but small, smaller than the physical size, we can think of them as we think about negatively charged hydrogen ions as one particle. And then we can couple them we can make them into a band and couple them in the same coupling mechanism that we had before, and that will lead to the same detachment of the lower band from the upper two. So by that, we managed to create here an insulator. It's a gap from the rest of the system. It's an insulator, but it's a featureless insulator. It's not topologically ordered in any way. So this is this basically concludes the argument that fragile bands are not protected against interaction from being separated, and just for the topology that gives rise to a fragile band is not enough to disallow the formation of an insulator at quarter filling. It's quarter because we had 4 bands and we fill just lower ones.
Sorry, Ady, there is a question by Christopher Mudry. Hi, this is Christopher Mudry.
Hi, good to see you, but I don't see you.
Yeah, I have a question regarding the trion.
Yes.
Do you need so your trion is the most likely place where you find a trion is at k equal to 0 in your construction. Do you need to have a threshold for the bandwidth over which the dispersion of the trion might not be good at large center of mass of the trion? So do you need a width over which you know that the trion exists?
Yeah, and that width in momentum space is related to epsilon 0. So epsilon 0 is the minimum of the trion band.
Yes.
And we need the trion band to be to exist safely until it meets the other band, the fragile band that we want to give.
So do you make sure that this is the case, or you just did you check that the self-consistency is working in your model?
Yes. We can take epsilon 0 to be as small as we want, and yet keep the pions bound enough. Yes, we check that. There are enough degrees of freedom here to allow for that. Okay. So you're sitting at the GGI, right? Yeah, good. Now I see. Any other questions? So now let me move to twisted bilayer graphene. In twisted bilayer graphene, you know, we have two layers of graphene twisted a little bit with respect to one another in such a way that the close to each, so the K points of the two layers are very close to one another. The twist make them slightly shifted, but the twist is very small, like 1 degree. So they are only slightly shifted with respect to one another, and the K prime point is very far away. If we think about the two K points alone and look at the mini Brillouin zone that they create, we get a fragile structure. They are two Dirac points that have the same chirality, and you can understand that because both of them are K points, and they're just shifted a little bit relative to one another. So in principle, we can, or naively, we can say, well, we can apply the same mechanism that we had before. First of all, let's merge the two Dirac cones into a quadratic band touching, and then do the, create the trions and have them interact with the bands and so on and so forth. But the first step was to bring the two Dirac points close to one another and merge them into a quadratic band touching. And that step fails in the context of twisted bilayer graphene, because moving those 2 points out of where they are will break the C3 symmetry, and we'd like not to break any symmetry of the system. So for a twisted bilayer graphene, the Dirac points are pinned to the K and K prime point by C3 symmetry, and therefore we need to find the twist. Sorry for the cliche pun. We need to find the twister on this problem so that we'll be able to apply our method. Now, our method starts from having a quadratic band touching. So somehow we need to take this Dirac point here and this Dirac point here and their copies, and turn them into a quadratic band touching without breaking the C3 symmetry. So the way we found to do that is complicated, but not very much. At the endpoint, halfway between K and K prime point, we construct new Dirac points. We construct two positive chirality Dirac points at the endpoint and two negative chirality ones. So altogether, no chirality is generated here. Now we take, of the -2, we take -1 to here and -1 to here, which leaves us here with a quadratic band touching, which we will be able to gap later with our mechanism. But we sent out -1 to here and -1 to here. Now this processing is done in entirely C3 symmetric way, and therefore we got -1 from here, -1 from here, -1 from here, altogether -3. We started from +1, added -3, we have now -2. -2 means a quadratic band touching, we're in business. We have -2 here, -2 here, and +2 at the endpoint. Each one of those quadratic band touchings can now be gapped by our mechanism, which we need to construct in a C3 symmetric way. But nothing prevents us at the level of principle from doing that. And I should say, this mechanism, as you see, is not unique to a twisted bilayer. This mechanism allows us also to gap a single layer graphene without breaking the C2T symmetry or the C3 symmetry that keep the Dirac points of graphene protected against gapping. So this is a mechanism that allows us to gap the Dirac points in graphene by interaction. And I should say it's not the only one. Actually, Ady Stern and his collaborators a few years back found a way to do that, which looks very different, to gap the Dirac points in graphene by having interactions, which may be an indication to a point which I'd like to emphasize. What I showed to you is that those fragile Dirac cones are gappable by interaction. And I showed it by introducing a mechanism which is, tailor-made. It's a designer mechanism. But it's not necessarily the only ones. Once we show that it's possible, there's no reason to expect that this is the only possible mechanism. And I imagine that there are others which we haven't constructed. So I think it's a good time to summarize. What I told you that a fragile topology lives up to its name. A pair of fragile bands may be gapped by interactions without breaking any of the symmetries and without resorting to extra bands coming from higher energies. Put differently, you can construct a featureless insulator with no breaking of symmetry and no topological order in a half-filled pair of fragile bands. So that's what I wanted to say, and I thank you for your attention.
Ady, for the nice talk. Maybe we wait for some more questions.
Can
May I ask
can
a question?
one more? Sorry.
Sorry. Ady, thank you for the very clear and nicely presented talk. I had a question about particle hole symmetry, because your pictures of tryons look particle hole symmetric. So I was wondering why there were two tryon bands with particle hole symmetry there. Is it because you assume the interactions break particle hole symmetry, or?
So,
Is there something else?
you mean this picture that looks
Yes.
particularly symmetric? Yeah, this was cropped from Google Images, but the construction we constructed is not particularly symmetric. We do have 2 electron pockets and 1 hole pocket. We don't have 2 hole pockets and 2 electron pockets, and therefore our construction allows only for 1 type of trion, the negatively charged one. You can imagine what you can think what will happen if you have more than 1. That probably you can construct a situation. I detach this band from the other 2. Basically, I gave the blue band the responsibility of band touching with the higher one, and probably with having another band of trions, you can complete the gapping in a particularly symmetric way. That's not what we did.
Okay, thank you.
Are there more questions?
Actually, can I ask something?
Sure.
So actually, if we add symmetry, so we can can we in general make the fragile topology a strong topology?
Could you say that again? I didn't get the question.
Oh yeah, I'm just saying that suppose we add more symmetry to the system, can we make the fragile topology a strong topology?
I think we can, yes. In principle, I think we can.
Then it would be interesting to check whether the interaction will turn on actually break that necessarily break that added symmetry.
Yeah, I agree. It would be interesting. I think you can. So you think can we have a pair of bands which are fragile, but also have some strong symmetry? So let's see, what do we mean by that? We can mean that there would be a let me get to. We can mean that there would be edge states, between in the gap here, but that won't affect us much because we were looking at the Dirac points which are in the middle of this coupled states, coupled bands. So I think the interesting question is, can suppose that you add another symmetry, would our gapping trions necessarily break that one?
Yeah.
So yeah, it's an interesting question.
Yeah, actually, I have a specific example. So for example, the Hopf insulator. Well, I mean, there's something called a Hopf insulator.
Yes.
So that one is a fragile topological insulator, but actually by adding some maybe a bit weird symmetry, actually that can be made a strong or well-defined topological insulator.
Yeah, it could be nice to try and work out this example.
Okay.
Yeah, it's not something I worked out anyway.
Okay, thank you.
Are there more questions? So, Ady, I have a question.
Sure.
So I'm not sure I got the what are the consequences of your result? I mean, is it a special thing of, so you are interested in bilayer graphene, or you think it's kind of more general phenomenon? And so the point is that I don't know very much this work on fragile bands, and so I cannot really value the relevance of your result. Can you say something about this, please?
Yeah. You can ask this question, as I said, for in two directions. You can first ask about this concept of fragile topology. How strong is it? So you know the statement about fragile, about these two bands that I showed you there, what you see here, is if you couple them by C2T symmetric coupling, you cannot. And you have one charge out of 4, so you have a quarter filling. You know, here you have 4 bands, so each unit cell have 4 states, and if you have if you fill it with 4 electrons, the system is full. Another question is, for a quarter filling, can you have an insulator? And at the non-interacting level, the answer is no. And what we show is that the interacting level you can. Now you know, with interaction, sometimes you can, sometimes you cannot. And sometimes, and there's also a third possibility, which is you can, but only with topological order. So here we show that you can have an insulator only with interactions. Non-interacting, at the non-interacting level, this would always be a semi-metal. Or maybe you can make it a metal by moving the Dirac constants up and down. But you're not going to have an insulator. Interactions allow you to have an insulator. That's the significance. So now, is it surprising that, you know, we went to this question, I think, tabula rasa, no? We had no, we really didn't know the answer. So I cannot say whether we were surprised or not.
Okay.
So anyway, that's the question and the answer.
Okay, thank you very much. So are there other questions? Okay, if not, let us thank the speaker to the extent we can online, and and so goodbye. Okay,
Thank you very
thank
much.
you very much, Ady.
We'll see one
Okay.
another later on
No,
this week.
you see, we know you. That's something more than no.
I don't hear you well, Andrea.
So we have an, and so we could clap you. We could clap. This is a thing in online seminars. Okay, thank you. Bye bye.
Thank you very much.
Bye bye.